In this video, we are going to discuss antiderivatives. Of course, so far we've spent a lot of time. What is the derivative? What is the derivative? Here is a function f. What is its derivative? It's time to start working backwards. We've spent so much time with creating the derivative that now we're going to do the antiderivative, where you would start with the derivative function and ask, where did it come from? So our learning objectives are all about these antiderivatives. We would like to be able to find the general antiderivative, and we would like to use some initial conditions to determine a specific antiderivative, but we can also use them to examine some motion. Quick recap of things that we've done before. Your initial function is f of x equals x squared. What is the derivative of x squared? Okay. G of x is cosine. What is the derivative of cosine? Okay, so in a lot of ways, we're just going to be thinking about, if we already have the derivative, work your way backwards to see where it came from. For example, if we start with the derivative 4x cubed, where did 4x cubed come from? Yeah, that's going to wind up being x to the fourth. What about secant squared? Secant squared is the derivative of tangent. And so knowing your derivative formulas, knowing your derivative rules will, of course, help it'll make it significantly easier to identify the antiderivative. But here's one thing that is absolutely critical that you understand. These are not the only answers. We got this answer of x to the fourth, and true, the derivative of x to the fourth is 4x cubed. What is the derivative of x to the fourth plus 3? It's on our left, f prime of x, 4x cubed. What about the derivative of x to the fourth plus 32? It's also 4x cubed. And what about the derivative of x to the fourth minus pi? Same. When we take antiderivatives, we are going to always encounter, always encounter plus a constant. Because this whole piece of x to the fourth could have been plus any constant number, it could have been minus any constant number, and when you take its derivative, you still wind up with 4x to the cubed. 4x to the cubed. 4x cubed. Same thing with tangent. It's not just tangent of x. That is one correct answer, but we could have tangent of x plus 1, plus 2, plus 0.13, plus pi, plus e, plus any real number you want. Do not forget, when you are taking antiderivatives, you will always include plus c, some constant. So the question was asked, can you just pick some random number, like plus 3, plus 7? The short answer is no. Going back to our learning objectives, it said determine the general antiderivative. Your general antiderivative is the plus c for some constant. Depending on other characteristics, though, it might be possible to figure out what that constant actually is. And that will be the specific antiderivative. We'll come to figuring out some of the specific antiderivatives, but first, let's do this one. What is the general antiderivative for f of x equals cosine of x? The antiderivative, which we will use a capital F. So we're basically saying what will give you positive cosine for its derivative. That's negative sine of x plus some constant. What about x to the n? Well, perhaps it would be easier if we think of a specific number. Just as an example, what if it were x squared? What function will give you a derivative of x squared? Of course, we know it has to have an x cubed component, right? Because we're going to have to subtract off 1 for the exponent. Okay, so we could start off with x cubed, but if we take the derivative of that, we've got to fix the coefficient problem. 1/3 times 3 would cancel each other out, and we'll wind up saying plus a constant. This would be our general antiderivative for x squared. Let's generalize that, though. Whoa. Let's generalize this so that instead of being just x squared, what about n? The important thing to keep in mind, 1 over n times x to the n, okay, plus c. That's what students are telling me. When we were using x squared, did we wind up with 2's? No. So your intuition of 1 over n needs to be adjusted a little bit. N plus 1 fixes that issue with making sure we get the correct numbers. And so there we go. We have a formula for the general antiderivative. Looking toward the future, our next unit is on integrals. Integrals are, well, they're just massively connected to antiderivatives. And so a lot of the things that we'll be working on with our next unit are creating formulas, using formulas, interpreting the results after we've done formulas. You know, pretty much how we started off right away saying, here's what the derivative is, and we did all the stuff for creating understanding what it is, and then doing shortcuts to get the answer faster. We'll run through the same thing with antiderivatives and with integrals. All right, so now that we have like this little formula, let's actually use it for C. What is the antiderivative of x to the negative 4? Negative 1/3 plus the constant. And we've got our answer. Okay, what about this? What are all the functions such that the derivative is equal to 4 cosine x plus 4x to the 6 minus x to the 1/2 over x? You mean we have to work backwards through quotient rule? That's crazy, Fry. What are you doing? Well, remember how a lot of times if you simplify some of the algebra, it makes it easier? Let's simplify some of this algebra. We have 4 times cosine of x plus, what happens if we divide out by that x? We wind up with 4x to the 5th minus square root of x over x, so that's x to the 1/2 over 1, which is x to the negative 1/2. And so let's consider and think through some pieces. What is the antiderivative of 4 cosine x? Okay, that's negative 4 times sine of x, because the derivative of sine is cosine. But why do we have a negative? The derivative of sine is cosine. So if we take the derivative of positive sine, we get positive cosine. This, your intuition, didn't quite match up. Intuition's great. Make sure you double check it though. Okay, what about this next part? What would be the antiderivative of 4x to the 5th? Remember how we were just using that formula that we just looked at and said if we've got this type of a power, we can kind of use that as our tool to help us out with some of these pieces? Well, instead of having a 1, we can use our coefficient of 4. And then 5 plus 1 is 6. 5 plus 1 is 6. And then we can subtract and say 1 over negative 1/2 plus 1. Negative 1/2 plus 1 would be positive 1/2. And so 1 over 1/2. We'll simplify that coming up. And then negative 1/2 plus 1, positive 1/2. Well, what's 1 divided by 1/2? Okay, so that part then was our 2. 4 over 6 we could simplify and just say 2/3. And there we go. We have our function g of x. What did I leave off? Plus the constant. For an antiderivative, you will always have plus a constant because we don't know what they are. Okay, find f if f double prime equals 12x squared plus 6x minus 4. And then we'll also have these conditions, f of 0 equals 4 and f of 1 equals 1. All right, so let's start off. Obviously, we can see the format behind this is, if we're starting with f double prime, we will have to take the antiderivative to get f prime, and then take another antiderivative to get f. So, let's take the antiderivative to get f prime of x. What's the antiderivative of 12x squared? Well, we're back to using that formula. 1 over 3 x to the third. So of course we can see a third of 12 is going to wind up being 4. Plus 6 times 1/2 x squared minus 4x plus some kind of a constant. So we get f prime of x equals 4x cubed plus 3x squared minus 4x plus a constant. Next, take another antiderivative. What's the antiderivative of x of 4x cubed? That's x to the fourth. What is the antiderivative of 3x squared? X cubed. What is the antiderivative of minus 4x? Minus 2x squared. Plus, what's the antiderivative of a constant? Constant times x. Plus another constant. And so this piece we have written out in yellow is the general antiderivative. We are looking for a specific antiderivative, and this is where our criteria for the conditions will come into play. Now that we know the general formula, we can plug in some information. F of 0 is equal to 4. So if we plugged in 0, 0 to the fourth plus 0 cubed minus 2x to the 0 plus c times 0, 0 plus 0 minus 0 plus 0 plus d. What did we just figure out? D is 4. So by using this initial condition, we can now know that part has to be a 4. So hooray, that was beneficial. Let's apply, I like this color today. Let's apply the other one. If we plug in x equals 1, f of 1 is 1, so we'd get 1 is equal to 1 to the 4th plus 1 cubed minus 2 times 1 squared plus c times 1 plus 4. So 1 plus 1 is 2. Subtract 2 is 0. C plus 4 equals 1. So we subtract 4 and get C is negative 3. So we can now back all this part up even further and say, now we know C, and I'm not going to write the plus, we can say minus 3. And there we go. We have our function. The specific antiderivative based on using the initial conditions. The initial conditions helped us figure out what the constant is supposed to be. Okay, example 4. Here is the graph of a function. Make a rough sketch of its antiderivative, given that f of 0 equals 2. Now, a lot of this is actually kind of based on some of our pieces that we did before. When we first introduced the derivative, do you remember doing pieces that said, here's a graph, draw its derivative? But they also had a couple other ones where, especially when we were looking at first derivative, second derivative, third derivative, for the velocity, acceleration, and jerk functions, we said, here are 4 pictures, which one's velocity, which one's acceleration? And we were looking at some of those derivative connections to see how they fit. This is similar to what we were doing before. Well, let's start off with one piece that's pretty obvious. F of 0 is 2. Okay, so what other information can we glean from this? Well, remember, we're being shown basically the derivative. So if the derivative has a height of 0, what does that mean? That's a critical value, indicating that we probably would have a maximum or a minimum. Well, the question is going to become, is it supposed to be a minimum, where we're connecting like this? Or is it supposed to be a maximum, so we're connecting like that? How do you know? Specifically, this whole region is under the x-axis, which means it's negative. What does a negative slope mean? The function is decreasing. So this is a way of telling us, for this interval from 0 to 1, we have to have a decreasing function, and then have a horizontal tangent line, followed by a positive slope. What does it mean for the derivative to be reaching a peak? That's an indicator for an inflection point. This is a piece where remember this y equals f of x is the first derivative. So if the derivative has a horizontal tangent line, that means the second derivative is equal to 0, which tells us we have inflection points, where we've got a possible change in concavity. So looking from here, we can see it is a positive still. So, where's my eraser? From 1 to 2, we have to have it be increasing and have it be concave up. But from 2 to 3, it's going back down, but it's still above the x-axis, which means it's still increasing. The derivative is still positive, so our function is still increasing. It's just not increasing as fast. That's what causes our change from being concave up over to concave down. You see the change in the concavity? Until we reach 3, another place where we're crossing the x-axis, so that's another maximum for this point. Then we've got negative. A negative derivative tells us we have to be decreasing until we get to 4. That horizontal tangent line then tells us we have a change in concavity. So it's still decreasing, it's just not decreasing as fast. So we have to change from concave up over to concave down. I'm sorry, it was concave down. We're changing to concave up. I said that backwards. And then we can see that this is limiting, or at least it appears to limit towards 0. That limiting towards 0 is telling us we are limiting also. And so we've got a general sketch of our graph based on the information we could tell from looking at it. You just have to keep in mind, what is the connection between the derivative and the original function? What is the connection between the derivative and the second derivative? And if you can bounce back and forth interpreting them, you can fill in the details with what the picture should look like, what the graph should look like. Here is our last example. This is geared toward our learning objective of being able to describe motion by using antiderivatives. A ball is thrown upward with a speed of 64 feet per second from the edge of a cliff 384 feet above ground. Find the height above ground t seconds later. When does it reach its maximum height? When does it hit the ground? Okay, so let's start by thinking through some pieces. What in the world is going on? Okay, so we're throwing a ball. It has speed. Okay, so when you throw a ball, what is this? That's velocity. Absolutely. It's important to recognize that we have velocity. And so when you throw a ball up into the air, well, if you're standing on the edge of a cliff, it's telling us we're starting off originally. This is the height at time of 0. So we could say h at time of 0. So find the height above ground t seconds later. Well, of course, if we can create the equation for the height above ground, then we can say when is the maximum. We can say when does it hit the ground. Those are all things that we can figure out. But it's going to be based on the idea that we will need this equation. The big hint that we have is a piece that, especially for people who are going into physics, for going into a lot of pieces with engineering, here's a fact that you'll want to remember. The acceleration of gravity is 32 feet per second, or per second squared. What is that? Gravity is acceleration. And so what we're noting is we know what the acceleration already is. We have velocity, and we are searching for the position function. You notice the connection between first, second, third derivative, or first function for acceleration, antiderivative for velocity, antiderivative of antiderivative for position. We can work backwards from what we were looking at before. So this is whoa, I don't know what happened there. Nope, Nope. Nope. There. Okay. So we're going to start off by saying the acceleration function. Acceleration due to gravity essentially is constant. We're going to say that's 32. Well, knowing that acceleration, we would have that is the derivative of velocity. So take the antiderivative to get the velocity function. What's the antiderivative of 32? 32, well, we're using time instead of x, so 32t plus some constant. Why do we have the constant involved? Okay, but we are fortunate to know the ball is thrown upward with a speed of 64. That tells us at a time of 0, when the ball is initially thrown, time of 0, velocity is 64. So if we plug in time of 0 and the overall velocity is 64, what does that tell you about c? C is 64. So we will come back and now say 64. Knowing that velocity is the derivative of the position function, use the antiderivative to get your position function. What's the antiderivative of 32t plus 64? 16t squared plus 64t plus some constant. But once again, we also know when time is 0, the height is 384. So at a time of 0, the overall position is 384. C is 384. Whoa, there, there. And I can't magically turn a C into a 3, so 384. And so find the height above ground t seconds later. Check. We've got that. Where does this reach, or when does it reach its maximum height? Well, maximum height, of course, maximum is telling us first derivative is equal to 0. And so we can come right back and say, when this piece equals 0, that's when we reach the maximum height. So at a time of 2. Okay, so second part, it reaches its maximum height at a time of 2. And we've got that part. Does it ask what the maximum height is? No. It just says, when is it? Of course, if the question did ask, what is the maximum height, we would have to take the time of 2, plug it into the position function, and get that answer. Fortunately, we were not asked that, so it's not extra work for us. But it's right there. The technique is basically the same. Last piece, when will it hit the ground? Okay, so if it's going to hit the ground, that means it's coming back. Well, considering that this is a piece that we threw directly up in the air, and now it's coming right back down, we have this piece then that we're noting is, well, I guess we should say it this way. We've got the cliff. If we regard this as being thrown directly up in the air, and then landing back where it was originally thrown, we are looking at when does it return to where it is. Well, just because of the symmetric nature of a quadratic being an even function, we would wind up with this piece. It returns to its height another 2 seconds later. So it's going to reach this part at 4 seconds. But if we're reading this as it got tossed over the cliff, When does it reach a height of 0? Well, we can say it's going to reach a height of 0 when that's true. When does the position function equal 0, which is the height of 0? So we're saying then 0 equals 16 t squared plus 4t plus, and how many times does 16 fit inside 384? Plus 24. Okay, can we factor that? Two numbers that will multiply to 24 but add up to 4. All right, if you don't see one right away, why don't we try just using quadratic formula? Okay, so if we're using quadratic formula, we would need time is negative b plus or minus b squared minus 4ac all over 2a. So negative b is negative 4 plus or minus the square root b squared 16 minus 4 times 1 times 24 all over 2 times 1. So 16 minus 4 times 1 plus 24. Well, 4 times 24 is 96. 16 subtract 96 is negative 80, and I hope you see the problem with that. We can't take the square root of a negative 80. This is a piece that does not factor. So this is a piece that wouldn't have an answer. Why is it coming out that way? Well, a couple different answers. Did we make a mistake? Did we lose a negative sign somewhere? Could it be that the thing actually does not have an answer? Could it be that if you actually throw it where it's following a parabolic arc, we would have a different function? Do you care? Valid question, I guess. Well, as I read the problem, we're saying this is thrown upward, which to me says it's being thrown directly upward. If we were actually throwing it at an angle over the cliff like this, we do not have a vertical acceleration of 64. We do not have a horizontal acceleration of 64. We have this diagonal acceleration of 64. And to be able to answer questions like this, when you're talking about a diagonal acceleration, we would wind up using a lot of work with matrices. We would wind up doing a lot of stuff with vectors. Welcome to a lot of the things that you will do in Calc 3. You will come back and do a lot of these things, but vector calculus is typically the third course in calculus that people take. So there we go. As I'm reading the problem, as I'm understanding it, the intent of the problem is you throw the ball directly up in the air. And so that means it's going to come directly back down. With the symmetry, it's going to be just another 2 seconds later. And so we would have it hit the original spot on the ground at a time of 4 seconds. Please note our learning objectives. Keep them in mind. Can you use some logic to determine the general antiderivative? Can you apply some initial conditions to figure out the specific antiderivative with our constants? And the tough one, could you relate some pieces between velocity, acceleration, position function with their antiderivatives to be able to describe some pieces with motion? If you can do those things, you're all set.